Hi, welcome to another edition of Fun with Physics, the Universal Law of Gravitation edition. This PowerPoint I'm going to proceed through. At any point, if I'm going fast, you need to raise your hand. Anything highlighted in yellow, you should write down. So you have this paper and we're at this first line. You're going to need to keep up. Then the second line, notice there's a blank, a blank, a blank, a blank. I'll be pointing things out and talking during the video. So let's get started. So, Einstein said gravity warps space and time. There's a demo with a tarp that we show with a weight that warps fabric. This is something Einstein theorized. So let's get going, and it's the basis for gravity. So yes, everything falls because of gravity. Gravity is actually an acceleration, but there is a force of gravity. So you have that one word up here to write down, gravity. Gravity is what makes the Earth round. The pull of gravity and its spin has made the Earth in its spherical shape. It is a little bit wider at the equator, so it's not a perfect sphere, but we model it as a sphere. So you can think of the Earth as a basketball that's been pushed down just slightly. So it's almost a perfect sphere. So your next line, you have a couple blanks, and the word mass is filled in for each one of those blanks. So that should be pretty easy. Mass attracts mass. It's like a magic force. Any mass in this room is attracting another. But as I said yesterday, because the Earth is so big, it pulls everything down. But all mass attracts other mass, magically. These are two stars here. They're so big that they actually attract each other and they spin in a circle. They pull on each other and they hold each other in this bond that's almost unbreakable. The modern space telescopes we use have allowed us to get these pictures, which are phenomenal and actually mind-boggling. The field of astronomy and astrophysics is actually quite interesting for students to look at, to study at college. The falling apple. So you've got a couple blanks. Look here, here it says Galileo said, up here Newton discovered. So Newton discovered on your paper, and then Galileo said. In yellow is what you should write down. It's been said, I don't know how true it is, that Newton saw an apple fall, and that's what made him think about this whole gravity thing that we now use today. I don't know if it hit him in the head, but he saw an apple fall out of a tree and wondered, what really makes that apple fall? Why did it have to fall? That's where he came up with the idea of gravity. So the only thing is, what's the force? Gravity is the force that makes everything orbit around something else. In order to accelerate, you have to have a force. So when you go in a circle, you accelerate because you change direction. So Newton noticed that the moon moves around the Earth in a circle, all because of gravity. So next line, you've got quite a bit to write, and it says, if the cannonballs, you can find that on your paper, if the cannonball, if it were fired slow with a small speed, it would hit the Earth and follow a parabolic path. Down here we have an animated demonstration. I shoot slow, it won't go very far. You won't get all the way around the Earth. So right now I'm going to ask if anybody needs me to pause the video, but I'm going to proceed. Does anybody need it paused? Raise your hand. Here are the next two lines. If it were fired faster is the key word. If it fired faster, it would go farther. No kidding. Now here's the trick. If you fire fast enough, a cannonball would make it all the way around the Earth and hit you in the back of the head. Something you probably won't want to happen. Again, right now, if somebody needs me to pause the video, please pause it. But for length of this video, I'm going to move on. This is interesting. Space shuttles are launched to 150 kilometers. So that's just a little under 100 miles above the Earth's surface. They actually are still feel the effects of our gravity, it's just less. So they don't get away from gravity, it's just less. And we're going to talk about why they actually perceive to be floating. So the next thing is, it says every second the moon drops 1.4 millimeters below a tangent line. If we were to turn gravity off, the moon would fly off straight and tangent. We said that in the last quiz. But because we can't turn gravity off, the moon keeps getting pulled around the Earth. It actually falls around the Earth. But if we could turn gravity off, at this point, the moon would fly straight and we'd lose the moon, which would make a lot of people sad. If anybody needs me to pause the video, please let me know. Next is the title of the falling moon. And there are several spots in there. Remember, when you move in a circle, you have a linear speed, and because you're going around a circle, you're rotating or revolving. You have a rotational and linear speed when moving in a circular path. The moon has a high enough speed that it doesn't get pulled into the Earth. Has a high enough speed. So you need a high enough speed or it would fall into the Earth. I'm going to move on. The falling Earth. There's one line there to the right. It's right there under Newton's theory. Under Newton's theory, confirmed the Earth is not the center of the universe. You have a blank on your paper. And the next line is right here. All the planets actually fall around the sun. So nothing really, we're not rotating, we fall around the sun, but because we're going fast enough, we stay in a constant falling motion. You look at the bottom, these aren't necessary. But Mercury, because it's so close, has to be going really, really fast, 107,700 miles per hour, whereas the Earth only has to go 66,000 miles an hour, or we would fall into the sun. Pluto, on the other hand, is the slow puppy, only 10,000 miles around. It's so far away, it's not even on this animation because it's so far away. It can go really slow and it'll stay in orbit. So the closer you are, the faster you got to be going. Were there always 9 planets? There may have been more at one point, or there may have been less, but right now we have 9. So going into astrophysics would explain a lot of this. What would happen if Newton's tangential velocity is increased? If the Earth slowed down, it would crash into the sun, and that would be the end of us. If Neptune were going too fast, it would pull away from the sun and just fly off into this universe. Now we're down to Newton's law of gravitation, and every object attracts every object. Mass attracts mass. That's what you want to write down. And down here are some blanks. You have the force, you have something key, and I'll jump off this real quick, and I'll jump back to here. We're down to Newton's law, the force, and there's several blanks here to fill in. So getting back to the video, there we go. You have a few blanks to fill in. Raise your hand if you need me to pause the video. I'm going to move on. At the very bottom there's a blank that says Newton's law can be expressed as. Here's the formula, and these are subscripts. So if I write this, formula and put it on here, this is what you should have written down. There's a force between any two masses. This is a gravitational constant, and that's distance squared. So I'll jump back to the PowerPoint. So pause, raise your hand if you need me to pause the video. Flip the paper over, and you can see a statement, and there are two things there to so you have two blank lines. Please fill that in. And as I said before, if you look at there about the Sears Tower, it used to be called the Sears Tower, now it's called something else. When you go up in a very high building, you actually weigh a little less because you're further from the center of the earth. Moving on, it basically, you'll want to know you weigh less because you're further away. If you'd like to put down this thing right here, under this, if you'd like to fill in a blank right here and put down, because you're further away from the earth, the center of the earth, your distance from the center of Earth is greater. So you should write that down under that statement. I'll move on. Raise your hand if you need me to pause the video. This is some information. Gravity is not exactly 9.8 everywhere. In Norway, it's 9.819. In Mexico City, it's 9.779. So gravity is a little less because it's a little higher. The higher you are, the less gravity. So when you climb mountains, you actually weigh a little less. And not because you're losing weight climbing those mountains. It's because the gravitational pull is less. The farther you get away from the center of the earth, the less you weigh. Now, the constant. This is quite important. This is a number, and you're going to need to take time to write that down. So I'm actually going to pause the video right now because you have a lot to write down. So I've paused the video. Now I'm back and I've unpaused the video. We have an example. We'll show you how to do this math. You can almost do it without a calculator. There are some tricks to it. First thing is you want to write all the numbers down. So you're going to write down what I'm going to write on the board and ignore this. Let me write this down and then we'll pause the video. So I'm pausing the video and I'll explain this problem to you. So we've paused the video. Now I've unpaused the video. And notice I have 20 times 10 to the 19th as my answer. This is another example, and I'll show you this example on the board. So, if you follow what I do on the board, I'm pausing the video. Inverse square law. What happens is gravity decreases the further you get away because it has to spread out more and cover more area. When you're close, it can hit you. The further you get away, the less gravity can affect you. It's called the inverse square law. And that's a spot on your paper to write this down. So, if we go back and look at this, we're down to this area right here. And you have one little thing to write down, inverse square. What does that mean? Distance affects gravity a lot. It decreases rapidly. So you've got some things to write down here. There's just 2 yellow spots. The moon feels 1/60th squared the force of gravity compared to on the earth. So it's very small. That's what the moon feels when we pull on it. Another example is a campfire. There's nothing to write here, so just look up here. The further you get away from a campfire, the colder you get. Duh. Or the closer you are, the warmer you get. Because the heat has to spread out like this light does. When you're really close, you're very bright. The further you get away, the less bright you are because the light's got to cover more area. So when I'm close, I'm warm. When I'm far away, I'm cold. So the force decreases quickly when you get away from a planet. Think of a planet as a campfire. The further you get away, the weaker the force. Concert's another thing too. When you're close, you can hear it really loud. The further you get away, the softer the sound gets. So you've got to be pretty close to hear loud music because it decreases rapidly by the inverse square law. The inverse square formula is 1 over d squared. Now typically I like to do this. I really like to write the formula 1 over parentheses d squared. I'd prefer if you wrote that down. And the last couple things we have to write. There you go. This is the end of the video. So I can pause the video and we'll do a lot of examples with this. One other thing is we can use the inverse square law to see how much light planets receive from the sun. This is quite a bit of astronomy. So Pluto receives very little sunlight, and so does Neptune. The Earth receives the perfect amount of sunlight. That's one reason why we have life on this planet. All because of the amount of sunlight that hits this planet.